Hi everybody, welcome to My Physical World. Today we're going to be talking about the Earth's radiation balance. This is chapter 3 in maybe 20 chapters of talking about the physical environment of the Earth. Today we're going to be talking about the sun, and we'll talk about some information characteristics of solar radiation, including the electromagnetic spectrum. And we'll finish off part 1 talking about some human impacts of the radiation balance. Part 2, which will be a separate video, will be concentrating on temperatures and how solar radiation dictates temperatures. So I hope you enjoy these two videos coming back to back. And please like and share them. Yeah, that's where we're going to be today. So, have fun. Let's go to the classroom. Located 8 1/3 light minutes from Earth, burning at a temperature of 11,000 degrees Fahrenheit at its surface, its furnace at its core, fusing hydrogen into helium at temperatures approaching 27 million degrees Fahrenheit, is the sun. Think of the sun as being a very large fusion reactor. The sun daily throws its energy toward the Earth in what is called solar radiation. As Earth processes go, this radiation is the primary fueling agent. In order for life to exist, there needs to be a radiation balance system, where incoming radiation is equal to outgoing radiation. There are two nuclear processes, fission and fusion. Fission is the splitting of atoms. This is the process that nuclear power plants use. Fusion is the process of fusing atoms of one element into another, such as the sun fusing hydrogen into helium. Fission reactors are common today. However, because of the immense temperatures created by fusion, storage of energy has not been accomplished efficiently. When we talk about solar radiation, we are actually talking about electromagnetic energy, which is all energy traveling at the velocity of light, 186,000 miles per second, or 299,000 kilometers per second, in a harmonic wave pattern. From electromagnetic energy, we get the electromagnetic spectrum. It is basically light energy broken down by wavelength. Before we talk about the different parts of the spectrum, it is important to discuss some metrics. Wavelengths are measured in the metric system. Sizes this small do not make much sense in empirical units, such as inches. A picometer is 1 × 10 to the negative 12 meters. Angstrom is 1 × 10 to the negative 10 meters. A nanometer is 1 × 10 to the negative 9 meters. A micrometer is 1 × 10 to the negative 6 meters. A millimeter is 1 × 10 to the negative 3 meters. Shortwave radiation is the part of the electromagnetic spectrum whose wavelengths are shorter than about 300 micrometers. However, there is no real defined cutoff. even though it might be a little dry to listen to some of these numbers, but gamma rays are any wavelengths that are less than 0.03 angstroms. X-rays are between 0.03 and 0.06 angstroms. The ultraviolet rays fall between 0.2 and 0.4 micrometers. Visible light falls between 0.38 and 0.74 micrometers, with each color of the rainbow having values between there. I'll put up a graphic that actually shows what the values of each of the visible colors are. Infrared falls between 0.74 micrometers and 0.3 millimeters. Then we get into the long-wave radiation, such as microwaves. Their wavelengths fall between 1 millimeter and 1 meter. The even longer wavelengths of radio, those are anything over 1 meter, and there are many different classes of radio waves, some reaching many kilometers. The solar radiation distribution in the spectrum, 9% of the spectrum is made up of gamma rays, X-rays, and ultraviolet rays. 40% of the spectrum is visible light. 50% of the spectrum is infrared. And 1% of the spectrum is made up of anything that is beyond 2 micrometers in wavelength. The rate of energy production from the sun is 2 gram calories per square centimeter per minute. This is called the solar constant. A gram calorie is the amount of energy required to raise the temperature of 1 gram of water 1 degree. A Langley is 1 gram calorie per square centimeter. So the Earth's solar constant is 2 Langleys per minute. In terms of radiation, there are 2 laws of physics that apply. Any substance with a temperature greater than absolute zero, which is negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit, emits radiation. The cooler the object, the less the energy, and longer the wavelength values. An example would be comparing the wavelength signatures of Pluto and Venus. Venus has a very short wave pattern. The interception of solar shortwave energy by an exposed surface is called insolation. The amount of insolation for any geographic location depends on the sun angle and the length of exposure time. As this animation shows, the latitude of your position north or south of the equator affects the amount of insolation. The square is not changing size or distance. Only its position north or south is. Its area remains constant. However, if you notice, the area of its shadow changes as the square moves northward, and the intensity of the shadow is spread out. Solar insolation acts the same way. When the sun is at a lower angle, the energy is spread out over a larger area. so higher latitudes receive less insolation than locations at the equator. World insolation balance on the globe can be divided into zones. Equatorial, 10 degrees north and 10 degrees south. A large surplus of insolation. There is intense sun radiation year-round. Tropical, 10 degrees to 25 degrees north and south. Here is where you find the tropics of Cancer and Capricorn. Insolation is at a surplus. Subtropical, 25 degrees to 35 degrees north and south. This is a transitional area of surplus and balance. The mid-latitudes, 35 degrees to 53 degrees north and south. 40 degrees north and south is the boundary between balance and deficit. Subarctic, Antarctic, Arctic, and polar, they experience severe energy deficit and high insolation loss. Besides sun angle and exposure time, the atmosphere itself can have an effect on solar insolation. Incoming radiation is either absorbed or reflected. Water and land absorb 50% of incoming insolation. Clouds absorb 3%. And dust and gases absorb 15%. The total absorption rate is 68% of incoming insolation. Reflected energy is also known as albedo. Water and land reflect 6% of incoming solar radiation. Clouds reflect 21%. And atmospheric scatter accounts for 5%, making the Earth's albedo rate 32% of incoming solar radiation. Let's look at some general terms. Initial contact points. For gamma rays, that's about 95 miles in altitude. For X-rays, it's about 55 miles in altitude. Scattering. The turning away of shortwave radiation in all directions by gas molecules. Diffuse reflection. Scattering caused by dust and other particulate matter in the atmosphere. Downscattering. The amount of scatter directed back toward the Earth. Absorption. The incorporation of energy into gas molecules. Albedo. The percent of electromagnetic radiation reflected by an object. Long-wave radiation is absorbed and re-radiated by the Earth. Ground radiation is the admission of long-wave radiation by the Earth's surface. This is the most common form of long-wave radiation. Counter-radiation is the long-wave radiation returned to the Earth. When this type of radiation takes place and long-wave radiation becomes trapped, it is known as a greenhouse effect. Remember from our previous video, sensible heat is heat measured by a thermometer. Latent heat is heat absorbed by a gas or a liquid during evaporation and melting. The total amount of heat which leaves the ground is 50%, 21% from long-wave radiation, 9% is sensible heat, and 20% is latent heat. The energy gained by the atmosphere is 68%, 50% by water and land, and 18% by clouds and dust. 8% of this energy escapes into space. We just went through a lot of terms and a lot of numbers, but in summary of the radiation balance, the net radiation is the difference between the input and the output of radiation. A surplus is when input is greater than output of solar radiation, and a deficit is when the input is less than the output insolation. Meridional transport is the movement of energy in terms of insolation from a surplus area to a deficit area. Can humans impact the energy balance? Yes, they can, through land use practices. For example, if it wasn't for forestry management, foresting would increase albedo in certain areas 20 to 70%. But reforesting returns a balance in just a few years. Urban uses have the most dramatic influence because concrete increases albedo and asphalt increases absorption. Many cities are starting to create green spaces in order to combat this problem.